What I want to talk to you today, though, is about the notion of identity and state in a distributed environment. Because the idea of identity and state takes on a different context in distributed computing than it does in our typical monolithic style of computing. So, just a little background, if you can see that up there. My name's Duncan. I work for Lightbend. I'm an engineer. We do this stuff. We have akka and play and lagom. You guys are probably familiar with a lot of it. Martin, one of our founders, is the inventor of Scala. So a lot of great people work there. My background is, I've been doing this, I don't know, 25 years or so, I guess. And I've been doing Scala for about 9 years or 8 years. And what I found, I was thinking about this earlier today, for me, Scala was kind of a gateway drug into distributed computing. It opened up doors and reasoning and ways to think about writing programs and understanding relationships between data structures and such that I had not come across before, because of that mixture of object-oriented philosophy and functional programming, mixing the two together. So that fascinated me, as well as the terseness of the code. I could write a case class instead of writing a immutable Java object and putting in hash code 2 strings and equals and all that fun stuff. So as I began to understand it better, I began to look out across the horizon and look at what we're trying to do as developers and the volume of data that we're going to process and that we are beginning to process. And about 7 years ago, a new view kind of came into view for me. So I want to talk to you about that a little bit today. And I don't like the term microservice, but it's the one that we have, so we have to run with it. So the question becomes, I think, what is a microservice? How do we define it? Because it means different things to different people, right? I would argue that Amazon Lambdas can be a small microservice, right? You can make a microservice that does just one thing, or you can make a microservice that does several things together. But I think one of the things that we've grown up on, or at least I grew up on, was this notion of being able to build an application where consistency is given, right? Where things like latency are not that big of a deal, and so forth. And things like transaction management are natural and they just work. When you move into, obviously, into a voluminous type atmosphere where the amount of data that you have to process far exceeds the capability of a single machine, that fantasy world begins to break down, and you begin to ask yourself, okay, how am I going to deal with these new problems that are presenting themselves? So at Lightbend, we believe in kind of isolating everything and making things small and digestible for a multitude of reasons, and we'll talk about that. And so microservice is one of these terms that I think has kind of come out of a bunch of different questions that have been asked, and there's no better word right now for it, so we'll just call them microservices. I think one of the amazing facts is Gartner said that the way that applications are built, this was about 2 years ago, the way that applications are built is now obsolete. It's not going to work anymore. When I was in the energy industry, we went from I don't know, maybe a couple 100 million records in our database to several billion overnight. Once we turned on our services, the amount of data that was coming in was it far exceeded anything that we had even, began to think about that we were going to be able to process. And within a matter of days, our system completely crashed because it couldn't handle the volume. And when that happened to me, that was a real eye-opener. So we had to spin up new machines, and my life became this continual nightmare of managing hardware and making sure a machine was up and running and checking everything at 2 and 3 o'clock in the morning. And I made a decision then. I said, this is not how I want to live my life, right? I do not want to live my life like this, so there's got to be a better way. And as I began to walk down that path and began to look at the options out there, I began to realize that what I had been taught, or what I had learned on how to build applications that manage consistency and state and all these types of things, those rules no longer applied. And so my initial approach was, okay, I have a situation here. I like to use the horse and cart example. I have a situation here where I have to carry more stuff and I have to move faster. So my first thought is, all right, I'm just going to get more horses. Right? I'll just get more horses, I'll get more carts, maybe I'll even try to do some of that stuff in parallel. And the problem is that I didn't need more horses and I didn't need more carts, I needed a car. right? I needed a vehicle that could go really fast and carry a lot of load and wasn't necessarily affected by weather and didn't need to sleep and stuff like that. And once I began to realize that the tools and the solution set that I needed was entirely different than what I was used to, I then began to realize, hey, I can't build things the way that I used to, right? There was a way that I looked at building an application, and so the whole reality, the whole landscape of what I was trying to do had to change. And I think that's one of the biggest problems with this, right, is we run up against this idea of change. We don't like change. We get comfortable, we learn what we learn, we know what we know, we want to move forward. We invested a lot of time. And in our industry, unfortunately, that just is not a reality. We have to accept the fact that we'll be in school for the rest of our lives and that we need to embrace change and adopt it and be willing to be flexible and pliable. If you're not like that, then that's going to lead you to failure. And that's why a lot of businesses fail. So this idea of microservices, one of the definitions that a lot of us like is the idea that you can create teams that are autonomous. They can kind of work in their own atmosphere. They can deploy. They can develop and do all these things independent of one another and push out independently. And that's a great way to view a microservice. It's more of an organizational approach, and it has some very valid value to it. But for our purposes, we're going to talk about it from a different position. We're going to talk about the context of microservices or smaller digestible. Microservices are a subset of SOA, right? So we're going to talk about this in the sense of distributed computing. So what I would say is that you can look at this idea of microservice and the idea of managing underneath the cover state and identity as a set of autonomous services, right? Autonomous services that collaborate with one another, kind of like we do, right? None of us in here have control over each other, but we kind of collaborate. We're autonomous. We can walk out and eat wherever we want to do and drink wherever we want to drink and then come back and aggregate together and create some kind of view that other people can consume. And that's the way we would recommend you look at designing systems, right? So autonomy, the Greek word autonomous, auto meaning self, and nomos meaning law. So the idea is your microservice, the service that you're responsible, is going to become its own self-governing kind of concept. And that implies a lot of things that we might take for granted. For example, if you're going to become self-governing, there's a certain amount of data that you need to have control over and that no one else can have control over, right? You're going to establish your own laws, you're going to establish how you're going to react with the outside world and so forth. So you have to be self-supportive in a way. You have to be able to make decisions independently, right? And extraneously from other microservices. You cannot be bound to them in any way. And it brings us to this notion of something called promise theory, which I'm a pretty big fan of. It's a philosophy more than a pattern, so to speak. But the idea is that in life, in systems, you cannot obligate somebody else to do something. You can say, hey, in order for me to be successful, you have to do X. But that becomes a huge problem. So as you begin to think about building these types of systems and you break them down and however it makes sense for your system or for your application, you begin to think of these autonomous services that act and work on their own behalf, independent of everybody else, and that they collaborate just like human beings is. That's why I like ACA and the actor model, because it kind of gives you that paradigm to think about. So Mark Burgess is the gentleman who came up with promise theory, and this applies to many different things in life, not just programming, but it's starting to make some inroads. DevOps uses it quite a bit, actually, and it's starting to make some inroads into how we think about programming. So the idea is you want to think in the terms of promises that lays the burden on you instead of obligations by laying the burden on somebody else. Because at the end of the day, you can only be responsible for what you are capable of doing. Right? If we're friends and you begin to rely on me, that will be your first mistake, right? Because I'm late and I make all kinds of mistakes. But the reality of it is you can't do that. You can't tie your success to my behavior, right? You cannot do that. That's a line for failure right away. So Obligations, when we obligate somebody, we lose control, right? We obligate somebody to do something of which we know before we even do it that there's no guarantee they're going to do it, right? They may walk out and get hit by a bus or quit, or who knows what will happen. So when you're building your microservices, you have to keep that context in mind. Autonomy, right, what we're leading for, or what we're striving for, makes information local, because you have to have that information locally in order to make your decisions, and it leads to greater certainty and stability in your service, okay? Whereas the opposite, obligations diverge. So they start from a well-known beginning, a concrete beginning. I'm going to ask you to pick me up at 9 o'clock. That's very definitive. But from that point on, it diverges. Who knows what happens? You may never have received my message, right? Fire and forget. That's what ACCA is all about. You may have received my message but decided that you don't like me and you're not going to come pick me up at 9 o'clock. There could be a numerous host of things that could occur that will mess up your ability to meet my obligation. So therefore, you're diverging from a solid start into a nebulous kind of like landscape. Whereas the opposite is true with a promise. A promise is more starting from kind of like an unpredictable beginning, where I'm going to say, okay, this person is going to promise to do something, but it leads to a more certain outcome. Right? The longer you get to know me, the more I deliver on my promises, the greater your trust will be. And this is just exactly how human relationships work, and this is how we work as groups. So why would programming be any different? Right? We're a distributed system in here at this conference. Right? This is exactly what we are, a distributed system. And as we begin to build systems, a lot of times we can take a look at our reality, nature, and take a look at how we interop as human beings and learn some lessons from that and apply that to what we're doing. So Mary Williams said, promises are not guarantees, guarantees are not possible. And I thought her tweet on this was excellent, and that's the reality of it. So if you begin to think like that, you begin to take a look at yourself and say, okay, I need to be self-sustaining. I need to live off the grid, so to speak, and have my service be able to do everything that it needs to do. So how can I do that? If I make the decision that I'm only going to deliver on what I know and speak to the world from my point of view. So that brings into us this idea of state. State is always one of the major problems, because in a monolith we can kind of have mutable state dangerously and share it to some extent. We can centralize it. But once we get into distributed computing, that becomes an issue. And I love this slide. We kind of find different ways to ignore that. We pretend that, okay, it's not that big of an issue. We'll manage it inside of actors all the time. We'll make certain services strongly consistent so we can leverage some of the old school ways of doing things. And at the end of the day, it's still a problem, because you have state that needs to be represented across the entire application. And you have all these different microservices. In a monolith, that's easy. There's only one, right? It's this big giant application. But in distributed computing, that becomes quite difficult. And you need to think differently. So I like to use my body as an example. I have arms and legs, right? And a torso and a head. They all have identity. This is my right arm. It's not my left arm. It has state. Right now it's moving, right? This is my left arm, same thing. But it still composes into a single unit called Duncan. And as we begin to think about our applications like that, we can begin to think about, this is one of the keys to resilience and elasticity, is the ability to take your state and diverge it across the cluster. It's not just technical, it's philosophical. It's the way that you think about how state is managed. A perfect example is a service. You might have an employee service where it's the aggregate root, and all employee-related activities come into this service, and it manages as a single, a POJA or whatever. Whereas in clustered computing or in distributed computing, the aggregate root would be the actual employee itself distributed across the cluster. So you have many single sources of truth which represent a specific employee, as opposed to a single service which is going to represent a group of employees. And the ability to do that is significant because now you can cluster it across multiple machines. You can implement resilience and self-healing, whereas if one employee, say actor, goes down, it can spin back up and recreate itself just the way that we do in real life. So this idea about managing state becomes real important. One definition is a computer or a program that keeps track of state and interaction by setting values. I mean, that's pretty obvious. We know that. What's interesting is as you begin to look at this management of state, depending on where you store it, whether you store it in hot access like memory or you store it in cold, the volume of data that you can process and the performance at which it's processed are inversely related. So if you keep it in memory, the performance is extremely high, but the volume you're going to process is lower because you're going to run out of memory. Whereas if you keep it in cold storage, the volume can be massive, but the performance is going to be really low. It'd be nice if we could figure out a way to get the volume real high and the performance real high. But that's something that we're continuing to work on and continuing to fail. So when we take a look at this and we begin to think about this as a distributed environment, when we look at these different services, one of the first things that we need to accept, and we accept this as human beings, but again, when we get into building computer, computational stuff, we want to kind of ignore it, is that we are always looking into the past. Whenever you tell me something, whenever I receive a message from you, right, that is going to affect me in some way. I can't pick you up at 9. Okay. That's great. I got to make alternative plans. When I receive that message from you, that is a historical message. It is not a valid representation of your current state. It is my last assessment of your current state, and I need to treat it as such, right? And I need to build barriers and protect, because that may be different. All of a sudden, you may show up at 9. Who knows what would happen, right? And so that's the way that I have to view it. So I'm always looking into the past when I receive a message from outside. The only place that is truly current is where I'm standing at, my own perception, my own reality of what I have control over. Everything else is from the past. And that's both terrifying and liberating. Right? It's terrifying in the sense that, wow, that information that I received may not be reliable, right? But on the flip side, it's liberating because now it's removed the responsibility of whether I have to worry about whether it's reliable or not. I'm going to make an assumption based on my relationship with you and trust of whether or not you delivered on your promises. This is very, very real. If you think about the military and you think about a battlefield and situational awareness, this is what they have to deal with, and we're talking life and death, right? Every time they send a drone out or whatever to take a look at what's going on, they're trying to get a sense of what's going on. And the same thing applies to business, right? Business can be brutal. Look at Netflix and Blockbuster. Blockbuster was a multi-billion-dollar company. It was the largest video company in the world. And Netflix came on the scene, and Blockbuster was like, who are these people? They send CDs through the mail? Are you joking? Right? We have stores all over the world. In fact, I even thought it was funny. My friend kept telling me, you got to go to Netflix. I'm like, are you out of your minds? I'm not going to order a CD through mail when I can drive down to Blockbuster. Well, because Blockbuster ignored that, Netflix ended up taking over, and Blockbuster went out of business. And even Blockbuster, when they tried to team up with HBO, it was too late. Right? Netflix had already established themselves, and now we all look at Netflix. They're a contributor to the industry. They've done so many things with streaming and all kinds of exciting stuff. So accepting some of these realities of how we view state and identity management become extremely important, not just to building a successful application, but also to our careers, right? Our companies. So this illusion of always striving to keep an absolute view of now across our application. Amdahl's law, Gunter's law, they both address this, and they talk about essentially in distributed computing, there's a diminishing return on parallelizing these processes, right? There's only so much you can get. Eventually, it kind of flattens out. And Gunter added to that and said there's an additional problem, and that's coherency. That's the latency that is natural in a distributed system, which makes this problem even worse. So at the end of the day, the point is that when you strive to fabricate something that just doesn't naturally fit in the environment, you're going to pay the price, and it's going to break, and it's not going to work. And the reason that we do that is because of the way that we've been taught. We grew up on Oracle or whatever it is, and we've decided that, hey, this is the way, or we've been taught this is the way to do it. Now, one thing I will mention, there is a lot of research out there now working very, very diligently on distributed transactions, CockroachDB, Google's F1 database, Microsoft's Azure relational database. And so I think that it's exciting, right? And I don't want to dismiss it because there's a tremendous amount of work. And I think that eventually that we may get back to a place where we can rely on something like distributed transactions because we'll be in a kind of like a sandbox where they'll work appropriately. But for now, that's not the case. And we have to realize that. So I think, like I said, if you haven't checked out some of those databases, you should. They're pretty cool, especially Cockroach. But for the most part, this reality it's not a reality for us. We can't make it happen. And latency is the biggest issue. It's kind of like federation across data centers. We get asked that question quite a bit. But RabbitMQ federates and Kafka federates. Okay. First of all, I don't believe that. But I mean, I know they say they do that. But the reality of it is we can only move at the speed of light, right? There is a latency that you cannot overcome, right? Until you figure out how to build a wormhole, you are done, right? And so the question becomes should I try to federate across data centers, or should I take a different approach where I'm going to have two separate solutions, one in each data center, that are independent of one another, and that the consistency of those two views are reconciled somewhere in the back end. I argue for that as opposed to trying to federate. So Pat Helland is a legend in distributed computing, and he said in a distributed system you can know where the work is done or you can know when the work is done, but you can't know both, right? And these are some of the realities that we have to learn to deal with and live with. And the problem becomes in distributed computing as we get into this area with microservices where it's like the perfect storm. You have your system, which is kind of like on its own little island and it's working great, and then you have the other system which is on its own little island, and then you cross this nebulous region called the distributed computing world, and this is where stuff goes nuts, right? You fire a message off and you never get a message back. Things fail spectacularly. You have no idea why. It's extremely hard to debug, right? We go back. I laugh because when I programmed in COBOL, whenever we would do debugging, we would always put a print statement in. And now when I write ACA, right, it's the same thing because the debuggers just don't work. Even the latest one that IntelliJ put out, it's awesome, but still, there's some ways to go. So again, I go back and put print line statements in. It's what I did 20 years ago, but it still works. So I guess some things never go out of style. So we have these islands that we build with microservices, and this kind of enforces a view on us. We have inside data, outside data, and between the services. Inside data is us. This is what we are responsible for. We control it. We own it. We are the origin of it and the maintainer of it. Outside data is anything that comes into us, any kind of perception. Outside data when you're driving down the street and you see all the billboards, and it's amazing that we don't have more accidents, actually, if you think about it, depending on where you're driving. But all that outside data, all that information coming in, all of that is historical. The second you process it, it's history, right? And then between asking the questions is a hope for the future, is the idea. So our argument is, I get this asked a lot, I want data locality, right? I have an ACA cluster. It's clustered across several machines. I have several nodes. I am processing so much data so fast, which I always want to quantify, that I need to have my data physically stored on the same node that my ACA system is on. So data locality. And the reason is because I have a clustered database, right? And I don't want to uncluster it. I want, I'm clustering Cassandra or Mongo or whatever, but I need to have my data located on the same physical, maybe even in the same JVM. And so our answer is always the same. Well, you can't. It's not going to work, right? Maybe if you use Cassandra and use the same sharding algorithm identically that akka has, then maybe. So what we will say is you need to have a copy of your data for each individual cluster or actor system, so to speak, right? That's going to be physically in the same place, because otherwise you're not going to have that data locality. But even a bigger argument is, let's really take a look at what you're trying to process, the volume that you're trying to process, to determine whether you truly need data locality. We've done hundreds of thousands of transactions a second with clustered Mongo or clustered Cassandra, where the data was not local to the akka instance. So sometimes these things, I think the best example is we kind of make up these problems that aren't real problems. Tiered architecture, and we use JDBC and that kind of stuff. And we wrote DAOs just in case we were going to switch our database from Oracle to Postgres or something. Now, honestly, in a big corporation, how many of you have ever done that? Not a single hand. I did it one time. I went from Ingress to Oracle. So the reality is the argument for separating those concerns really has nothing to do with the fact that I'm going to switch my database. It's more that the toolkit providers can kind of abstract an interface that's going to work with different databases. So it's the same thing here. Owning your state exclusively at first seems scary, but it depends on how you build your system. And we'll talk about that here in a second. The other thing is statelessness. A lot of us will think, okay, I'm going to have one system here, and I'm going to stick Kafka in between. I'm going to stick a queue in between, and therefore I can make my system stateless. And our argument is, while that works, and there's some, I think, good use cases for that, it's not necessarily the right solution for everything. Because what you're doing is you're pushing off the management of state to somebody else, in this case Kafka. Whereas inside your microservice, if you're using akka persistence or whatever mechanism you're using, you're controlling it, you maintain it, you have complete control over it. So the idea of a stateless application is kind of a fantasy. Again, as we draw closer to what the point of our discussion here today is this distributed identity and state. Another good concept inside of these microservice or distributed microservices, binding, right? Bounding your context. So if you're familiar with domain-driven design and Eric Evans' work, it's really good stuff. If not, I would definitely read it. But when you come to distributed computing, the model changes a little bit. And the aggregate root was the example I was using. In a traditional monolith, that would be a service, but in a distributed system, that's going to be spread out across the cluster, and each identity, each individual employee, if you wish, ends up becoming its own source of truth or its own aggregate root. So this brings us to the beast, right? Oh, it's up there too. Eventual consistency. That's what we end up dealing with. Nobody likes it. Everybody hates it. But it's a reality. And so my argument is, financial institutions, it's probably pretty important, right, for a financial institution to get your bank statement correct. Wouldn't you agree? I mean, if you reconcile your bank statement and you have $10,000 and then your bank tells you you only have 50, that probably is not going to work for you. But yet, even in an institution like that, they don't have strong consistency. You have bank overdrafts, right? So if I'm in China and you're in South America and we're doing debits and credits on the same account, there's a probability, or I write a check, there's a probability, however little, that we could get out of sync and we could have an overdraft. Same thing with inventory, back ordering, right? If you had a truly strongly consistent system, you would never have back orders, right? You would always tell the customer, it's out of stock, come back and try again. Or in the case of the bank statement, you would say you can't withdraw those funds because the balance is zero. In our world, eventual consistency becomes a reality that we have to deal with, and there are other ways to manage it by way of things like causal consistency, where you can add additional checks and validations and so forth to ensure that things are reconciled appropriately. But at the end of the day, eventual consistency essentially rules in distributed computing. And that's a reality that you have to accept, that I would say, don't fight it, embrace it, understand it, and learn how to live with it. It will make your life a lot easier. It's because of eventual consistency that you're able to do things like loose coupling, and it's because of loose coupling that you're able to isolate and bulkhead your microservices and build them on top of promises rather than obligations. So it's the sequence of interoperating philosophies that allow you to build these systems, which then in turn become resilient, right? Or elastic. You can auto-scale them, or you can self-heal them. It's because of that loose coupling. If we're tightly bound, then my ability to do that is impeded significantly. So what we call this in owning your own data is polyglot persistence. And that implies several different things. One is it implies that each microservice or each sliver of your application that's bulkheaded and isolated should store data that it needs, even if it's duplicating data from another service, and it should store it in the medium which is usable or appropriate for its use case. That might be Postgres. It might be a relational database, it might be Cassandra, it might be Redis, it might be, in memory, it could be a host of different things. It could be flat files, whatever works for your system, right? And makes the most sense is what you want to do. And so as we were talking about this is going to bring us into something called event sourcing. And again, back to Pat Helen. Pat Helen's argument is that the log, right? Bill did a great course yesterday, and he was talking about side effecting. And what is so functional programmers are no side effecting ever. It's, against the law. We will have to arrest you and throw you in jail if you do it. But there's one place where we side effect all the time, and it's natural, and we don't even think about it, and it's logging, right? All over the place, all through our application, incredibly useful. Would you not agree? Logging is useful. And so yet, that violates functional programming rule number 1. But who cares? Seriously, that's the thing that we have to think about too, is how stuck up on some of the stuff that we get, right? Another thing Bill said yesterday I thought was really awesome was the external API should be very functional, but the internal guts, right? As you're learning functional programming, you can evolve that over time. It doesn't have to be perfect to begin with. And it's so true, right? That's the whole implementation and interface pattern that we're used to. As long as I don't mess up somebody in the outside world, what do you care what I'm doing on the inside? Right? As long as I deliver in the time in agreement with our SLA. As Jamie said yesterday, resilience is not the most important business value, right? And my argument is they're two entirely different issues. Jonas's point of view is from engineering, Jamie's is from a business point of view. They both have extreme value. If I cannot provide business value with whatever I'm building, it doesn't matter how fast it is or how good it is. But on the flip side, if you can't get to my stuff, that's why responsiveness is at the top of the React manifesto. If you can't get to my stuff, it doesn't matter how much business value I garner. You can't get to it. It's useless to you. So they're both very, very important. Obviously, business value brings the money. That's kind of like the genesis, so to speak. But if you can't deliver, then it doesn't matter how important the idea is. So event logging. How many people in here are familiar with event sourcing? It's kind of getting to be known now. Good. So I'm not going to go through this in great detail, but the idea is the canonical example is your register and your checkbook, right? Everything is written as an event, append only. Why is event sourcing so powerful in distributed computing? There's one reason. Well, there's two reasons. The first reason is the key is very shardable, right? It can be a hash, and it's very easy to shard across the cluster. That's huge. So no matter how big your cluster is, the notion of using event sourcing gives you that ability. The second, I think, very, very usable thing, which is not specific to distributed computing, but it gives you a natural audit log. So when I was in the energy industry, we got audited all the time, and security was incredibly important. We did systems for the NSA at Fort Meade, and we would go back and forth. And everything had to be audited. So the initial pass when we use Spring and Hibernate, I had to use Hibernate and VARs. Are you guys familiar with that? It's a nice little plug-in for Hibernate, and it gives you auditing, right? And so you basically annotate a particular query or whatever, and it will audit that query and write the data to a separate table, which is kind of cool. But it's a pain in the neck because you've got to implement it for everything that you want to audit, whereas with event sourcing, auditing's baked in automatically, right? So you don't have to worry about any of that. So whenever I went before Con Edison in New York or, Fort Meade, and that was a requirement, all I had to do is show them how that worked, and they checked that off. Good. So I think that's super valuable. So I'm going to end up with a little example here that kind of gives you a sense for create, read, update, and delete. So we're used to, so let me just say one thing about that first. I am not saying you should never use the CRUD paradigm. I think that you need to take a look at your use case. If you have a use case where current state is the only thing that matters, you do not care about history, then CRUD is perfect, right? It works very, very well. The only problem you can get into it is if your volume gets really, really high and the complexity of your queries can cause an optimization problem or a performance problem. But I think the real issue with CRUD is not so much that, is if you do need to have any type of historical value which allows you to reconstitute your state and your identity in a distributed environment, you lose that with CRUD. Because things occur, you're doing in-place modification of historical data. So you're going to delete something or you're going to update something, and you've lost the record of what actually happened. And so in the shopping cart example, here's a CRUD shopping cart, and we add some items, we add the shipping information, we generate the total, and then before the customer decides, or before the order is shipped, the customer deletes something, they remove item 2. And so the total is changed, it's re-updated. The order line table, we delete that item from the table, it's gone, and so forth. And so we kind of have this view of reality. We have an order line table which has some items in it. At this time it only has 3 because we deleted one. We have a shipping information table, we have an order table, and we have a total. And what happens is our manager comes along and says, look, there's one of our products that isn't selling too well and we don't really know why. We're wondering if it's getting removed out of the shopping cart before the order is processed. And so we need to figure that out. And so our answer to the manager is like, well, I can't tell you that information, but in the current sprint, we'll plan to add auditing for that particular use case, and we'll implement it. And the problem with that solution is while that will work, it has a substantial implication or impact on the value of your data, because now you can only answer that question from the point that you've implemented that new feature forward. Right? You can't answer it historically because that data was deleted. Whereas in a reactive shopping cart, right, in a reactive model where you're using event sourcing, that data is captured from the origin of the system, the first day that you roll it out, right? So we have events. You're somewhat familiar with this, so I'm not going to go through this in great detail, but here's the same scenario. You have the items that were added, the shipping information. This is what our event stream looks like, okay? And so we have each individual action that is recorded as an event. And then the customer comes in, they remove that item, and that delete is not a delete. It's just another event that gets appended onto the historical log of what is occurring in the application. Now when the manager comes back and asks that question, well, first of all, the structural integrity of your data is sound because it's just a logging, right? And pendulum logging, so to speak. You can reconstitute history at any point through the life cycle of that sequence of transactions by simply replaying. And you can stop wherever you want to. You can even chunk pieces. You can start later in the sequence and chunk up to, say, let's say you have 25 events. You could start at event 10 and go to event 15 and look at the impact. So you can begin to take a look at your data in ways that were impossible with the other model. You can begin to project, and you can begin to answer questions that perhaps have not been answered yet. That's really the true business value behind it. You have fewer locks, and from a technology point of view and from a data access point of view, there's a lot of different advantages to doing it this way. On the flip side, if you've ever looked at most models that do event sourcing and you take a look at the data itself is usually serialized into the database in binary format or something, and so it's not the easiest to take a look at and so forth. But the advantages for a distributed environment are significant. If you haven't read this, Life Beyond Distributed Transactions by Pat Helen. It's a white paper. It's awesome. I highly, highly recommend that you read it. It gives a lot of interesting insight into this whole scenario. So this is really the slide that I'm trying to get to in my whole argument here about distributed identity and state. So I use the body example. I use the example of my arms. And this is exactly what happens in our applications. So we have the notion of state, right? State is, if we use like a rugby player, for example, if a rugby player, if they're currently healthy, then their state is healthy and their identity is a rugby player. When a behavior happens or something external influences the state of our rugby player, i.e. they get sick, they get the flu, right? Their state is now changed. They're no longer healthy, they're sick, and their identity has changed as well. They're no longer a rugby player, they're a patient, right? So they've changed their identity. So behavior affects state, and state's composition affects your identity, right? We see this all the time with our emotions. I'm happy, I'm sad, I'm depressed, I'm whatever. Some behavior in the external world affects my emotional state, and then my identity changes. You may not want to hang around me if I'm depressed, right? Or if I'm happy, maybe you're thinking, he's a nutcase, let's just get out of here. So this, in a distributed environment, we take in a monolith, we take this for, what's the word I'm looking for? Granted, right? It kind of all just works, it happens. But in a distributed environment, it gets broken apart and separated across a cluster or whatever. So we may have different entities, a rugby player and a coach and a judge or whatever they're called. They all are different identities, but they affect one another, right? And that's what we have to manage. So if we, just to kind of end the talk here, behavior is going to affect our state. That's the first thing that we need to understand. That's why actors are great. They manage behavior and state. And the result of modifying our state could very well change our identity as well. And considering that type of behavior across a distributed system is what we have to deal with now. In order to get what we want, resilience, elasticity, scaling, performance, and all those kinds of things, we need to think differently. So that was a long way around the mulberry bush, but that's pretty much what I have for you today. If you have any questions, feel free to ask.
We have a few minutes if
yeah.
you want to take questions.
Okay. Good.
Oh, okay, cool. Hi, here.
Hi.
So I'm still a noob with event sourcing, so please excuse my question if it's too beginner-ish. So one thing that I've had trouble with is introducing event sourcing or thinking about an event sourced microservice in a CRUD ecosystem, or even worse, when you have to integrate with third-party systems which are CRUD. Can you get some words about that?
Yeah, absolutely. There's a big piece of the puzzle that's missing with event sourcing, and that's how you project your data. So in event sourcing is really, you really need to think of event sourcing as a log, right? That's the easiest analogy that I can think of. And that does not necessarily represent how you want to project the data to the consumer. So CQRS, or Command Query Responsibility Segregation, is kind of like the second half or the evil twin that runs around with event sourcing. And this is where you duplicate data. And basically, you're going to store the data in projection format in some persistence mechanism that's suitable for that use case. In terms of third-party systems like CRUD systems, in fact, we just had a big client And their argument was, we've already optimized our system as much as we can, and we've cached data all over the place. And I'm like, no, you have not. Okay, your screen takes 5 seconds to load, which is completely unacceptable. Why is it taking 5 seconds to load? It's taking 5 seconds to load because you're hitting that Oracle database, which has your customer information in it. So that is your bottleneck. You spend all this time building out a clustered active system, which is lightning fast until you hit that bottleneck. Now, what you're telling me is you've pulled data out, not in projection format, but you've just pulled frequently accessed data out and you've cached it. That's not good enough. What you need to do is pull the results of the queries out that you're asking premeditatedly and store them in an external format that is designed for speed, right? So you're going to duplicate the data that's in Oracle, the most projected queries. You're going to pull that out every minute, and you're going to store it in Cassandra. Then when you come in and ask the question, you're not going to hit Oracle, you're going to hit Cassandra, and your answer is going to be almost instantaneous. And that's the breakdown. That's where they're like, well, wait a second, I don't understand that. They understand it, they just don't want to accept it, is the reality. You're asking me to give you Ferrari performance, in a Hugo or something, and it can't be done. Right? You have to make some modifications. So when you talk to that CRUD system, if performance is an issue, you may have to pull the data out and store it in a format. And this is where MySQL got its name, right? Everybody talked about how great MySQL is, and the reason is because they normalized everything, or denormalized, or whatever it is, flattened everything out. I always get it wrong. They flattened everything out, so they duplicated data, and they had lots of columns in their tables, and when you ask the question, you ask for a single key. So that's what I would argue. You're going to build a context around your system and around that CRUD system, and you're going to do whatever you have to do in order to get the performance you need. And if that means you got to ask select star from employee every 5 seconds and store that result in some aggregated projection that makes sense, then that's what you have to do.
Another question about event sourcing. So I understand event sourcing is great for logging purposes. Another analogy I use in the past is think of something like how Git or GitHub works, where your commits are the individual changes and your diff or blame, that's what the representation is up to by applying the commits. The one challenge there is that there's two things I think I see. One is that in the production application, for most purposes, you care about the latest projection. So there are some cases where you want to go historical, like logging or recovery or backups or something similar, but for most purposes you do want to operate on latest data. And the second is a question about performance, where as your history grows, it might take longer and longer and longer to derive the state, unless your database is some kind of caching mechanism or like snapshotting based mechanism. So two questions about, are my assumptions correct here? And also, since most frameworks that I know of at least are not really designed with an event sourcing database in mind and use it natively, what can you use? What kind of maybe database or other tools you use to actually have the event sourcing when you want it, but at the same time still get a benefit of the existing ecosystems, which all assume you're on the latest CRUD database?
Yeah. So the answer to the optimization of many, many events is snapshotting. That's exact. So you're going to snapshot current state, and you're going to put that into a database or in a separate table than the event history. That way, when you replay, you're going to go back to the last known good snapshot. You're going to reestablish current state, and then you're going to play the events from thereafter.
So it's possible, like when we hear about something like a temporal database, there's something it does natively. So by default, my queries would give me the latest state, but there's another syntax or something now. I want the historical dimension of this.
Yeah, well, that's totally different. I mean, when you have a temporal database that natively handles that, I can't think of the name of it off the top of my head, but that's an excellent way to go. But if you don't have that, if you just have Cassandra or Mongo or something like that, then you're going to implement a snapshotting mechanism, and that should be part of the event sourcing library. So for ACA persistence, that's part of it. It's very easy to do. You don't want to have to implement that yourself. But as I said earlier, if you only care about current state, like high frequency trading, okay, I don't care what the trade value was 5 seconds ago. All I care about is like now, right this second. And the volume at which I'm processing trades is so high, you know, that I'm going down into the L2 cache of my CPU and so forth. And so therefore, all that data I can just drop on the floor. We have customers that have processing so much data that the data scientists had determined the first 100 reads they can just drop on the floor and take the 101st. And then the next 100 they drop on the floor and take the 201st, right? Because the data, or the volume of data they were processing was so high, and they were still doing event sourcing with that. It's just they were doing every 100th point. We did that at the energy company, depending on the client. And the one thing that you have to recognize, though, when you start going down that path is you have to understand your data, and you may have to implement some smoothing algorithms. Because as you pull the data, it may be erroneous. You might get a spike, an anomaly of some sort. And that's where your data scientists really become super, super, super valuable. Because they understand the data, they understand the relational aspects of the data across temporal boundaries, and they can make decisions based on their knowledge of how the data should work and deal with those inconsistent breaks that occur.
Thanks.
Yep.
Hey, Duncan.
Hey.
Could you please talk a little bit about domain-driven design? How is this important in order to not get monoliths, or now called microliths?
Yeah, so I would say that there's a little bit of a difference in that microliths essentially occur when you have the two microservices that are bound tightly. And I'll give you a perfect example. My first distributed application was a microlith. And it was a microlith because the versioning that we used for ACA was abstracted out as a common library. So then Service 14, when we wanted to change it to use ACA HTTP, I couldn't, because I would break everything in my entire system. And I thought, okay, wow, how much of an idiot am I? That's kind of obvious, right? So I pulled the versioning back down in just for that service. That broke binary compatibility, right? So now I couldn't use remoting. I had to use REST until the other ACA version caught up. I mean, these are some of the realities that you have to deal with. But as far as domain-driven design is concerned, I think it gives you a way to think about and reason about behavior in your system. That's what I find very valuable about it. It gives you natural isolation, where you have anti-corruption layers. It gives you behavioral patterns where I have an aggregate, which is going to, basically control that type of stuff. And then you have your entities, which are things that you're just going to persist the data on. But what I would argue is Vaughn's book is, I think, a little bit more up to date than Vaughn Vernon's book on this stuff than Eric's, only because Eric's is 15 years old or whatever now. If you haven't read this, read Eric's first, then go read Vaughn Vernon's books. He talks about distributed meshes for aggregate roots and some pretty interesting things. That's what I would recommend. They are much more the expert than I am on that. Good?
Thank you.
Okay, thank you very much. Enjoy the rest of the conference.